everyone. This is the second part of the 15th lecture in the series Mathematical Methods for Economics. The topic for today is exponential functions, and in the first part we talked about the various areas where exponential functions are used. We talked about what it means for a quantity to increase or decrease exponentially. So what is the difference between an exponential relationship as against a linear relationship? And we also went through some mathematical preliminaries relating to exponential functions. Now, what I'll do is I just cited the applications, the various applications where exponential functions come in handy in the first part of the lecture. Now, let's actually get a little deeper into these applications. The first application is that of compound interest, and the result that we have here is that a savings account of rupees K, let's suppose you have rupees K which you put into your savings account, and the money increases by P% interest per year. This amount would have increased after T years to K times 1 plus P by 100 to the power T. Okay. So let's go ahead and prove this result. Alternatively, by the way, I can also write this as K times the amount in time period T can also written as K times, where K is the principal amount, 1 plus R to the power T, where R is nothing but P by 100. So to give you a sense of things, let's take some numbers. Let's suppose you have rupees 1000 which you deposit into your savings account, and this is deposited at 10% interest per year. So here you have R is equal to P by 100, which is 0.1. Okay. Now what will happen is, this is time period 0, you have just deposited 1000 rupees into your bank, and the bank is giving you 10% interest. So at the end of 1 year, how much interest are you going to earn? You're going to earn 10% of 1000, which is 100 rupees, right? Which is to say that at the end of 1 year, you will have 1000 plus 10 by 100 times 1000, right? Which is nothing but 1100 rupees in your bank. Now, you would say that, okay, I have put 1100 rupees in my bank now, so the bank should give me interest on 1100 rupees. And this is the beauty of what is known as compounding. You earn interest on interest, right? So what happens at the end of second year? You're going to earn interest, the same 10%, but now you're going to get interest of 10% of 1100, right, which is 110, and the amount that you have in your bank at the end of the second year will be 1100, right, plus the interest that you earn, which is 10% of 1100, and that amounts to 1210. Mathematically, this can also be written as follows, because we have just said that 1210, in this case 1100 I can take common, so 1100 times 1 plus 10 by 100, that is equal to 1210. Now note here, 1100 from the previous row is 1000, which is your principal amount, times 1 plus 10 by 100. So substituting for 1100 here, I can write 1000 times 1 plus 10 by 100, and the other 1 plus 10 by 100 will come from here. So that is nothing but 1000 times 1 plus 10 by 100, the whole squared, right? So I'm trying to write the amount that you get in any year as a function of the principal amount. I'm trying to reduce it to the principal amount. Then in period 3, what will happen? The same argument. Now you're going to earn interest, 10% interest on 1210, which is 121, and then your amount at the end of year 3 will be 1210 plus 10% of 1210, which is 1331. And this again can be written, you can look at these calculations here, this can be written as 1000 times 1 plus 10 by 100, the whole cube. So in general, what is happening? Look here, at the end of the first year, I have 1100 in my bank, right? 1000 has become 1100. At the end of the second year, it's 1210. At the end of the third year, it's 1331. And this mathematically, like 1100 can be written as 1000 times 1 plus 10 by 100, as I showed in the previous slide, the last to last slide. That is nothing but K, because K is the principal amount, times 1 plus R, right? R is nothing but your 10%, so 0.1. Similarly, 1210 we said can be written as 1000 times 1 plus 10 by 100 the whole squared. So remember, just notice here that the year that you have in the first column is the same power that appears here, right, for 1 plus 10 by 100 squared. So this then in general can be written as k, which is a principal, times 1 plus r the whole squared, right? And then for period 3 you will get the general expression for the amount in period 3 as k times 1 plus r the whole cubed, right? In general, we can write the amount in any time period t as k times k, the principal, times 1 plus r to the power t. So if you just compare things with the general form of the exponential function that we introduced, which is capital A times small a to the power t, then capital A here is nothing but your principal amount k, and small a is nothing but your 1 plus r, which is your fixed factor. And this is exactly the check I would like you to do. If you take the ratio of 1210 to 1100, that should be nothing but 1.1, because 1 plus r is your fixed factor. Similarly, if you take the ratio of 1331 to 1210, that again should be 1.1. So do you see, your quantity, your money is increasing at a fixed factor per unit of time. Now, this is in contrast to what you would have in a situation where you have deposited 1000 rupees at an interest of 10% per year, but let's suppose here you get simple interest. What do we mean by simple interest? It just means that the interest is going to be calculated on the principal amount, so that at the end of the first year you have 1100, which is 10% of 1000. At the end of the second year, you will have 1100 plus that another 100 rupees of interest, because 10% of 1000 is 100, so 1200. So what do you see here? When you have simple interest principle being used, then that means your account grows linearly with time, right? In every subsequent time period, your money increases by the same amount, which is 100 rupees. And this is the case of linear growth. So your account grows linearly with respect to time, and the amount in any time period is nothing but the principal amount plus the accumulated interest. So, for example, in period 2, the principal amount 1000 plus the accumulated interest as a proportion of time. So, here you have two time periods. So, accumulated interest here would be 200 rupees, right? That is the idea of simple interest. And clearly, you can see very clearly that your money grows much faster in the case of compound interest. Eventually, initially you will see some similarity in the values, but for higher values of t, your money is going to grow much faster. Now, the other example that I want to talk about is the case of population growth. So, if you have gone through the lecture that we had on linear functions, we had taken this data. We had taken the population for two time periods, 2000 and 2010, where the year 2000 represented time 0. And here you were asked to construct a linear function to estimate what the population would be in any time period, in any year. So, here we got the result for a linear function that p is equal to 17.8 times t plus 1053. Right? That is to say that in every time period, in every year, your population grows by 17.8 million, right? And that is reflected by the linear function here. So the question now is, when we take this annual increase in population to be a constant, which in this case is 17.8 million, is that a reasonable assumption? Is it reasonable to assume that population increases by the same amount in every time period? And here, if you were to just give it some thought, one would actually think that, if your numbers are growing, if population is growing, then there'll be more people to have children. And then also, if you think in terms of advances in the field of medicine, then you could think that the death rate is probably going down or maybe staying the same. And in these kinds of situations, why would you expect the annual increase in population to be a constant? So here we try to model population growth as exponential growth, and let's suppose population is growing at 1.1% per annum. Then we can model it here as exponential growth. For example, in 2001, the population, because 2001 is period 1, the population in period 1 would then be the initial population, which is 1053. Again, I'm using the same principles that we used in the example on compound interest, because population is growing at a rate of 1.1% per annum. So 1053 times 1.1 divided by 100. So that will be added to your initial population 1053, and you get 1064.58 million as a population for the year 2001. Similarly, the population for the year 2002 would, here again you see this compounding effect, and what do you see here? There is a fixed factor which is 1.011. In every subsequent time period, the population increases by a factor of 1.011, right? And if you look at these calculations, the population in time period 2 now becomes 1053 times 1.011, the whole squared, right, because this is time period 2, which is equal to 1076.29 million. And in general, I can write P of t as 1053, because that's my initial population, times 1.011 to the power t. Okay, mathematically this can be written as P sub t, population at time period t, is equal to P naught times 1 plus r to the power t, right? Here r is nothing but 0.011, 1.1 divided by 100. So you can see here that again comparing things with the notation for the format that we use for exponential function, this 1 plus r represents your fixed factor by which population is going to increase. Okay, another important concept that we have in population growth is that of doubling time. So let's look at this example. Here we have the population of, it's a fictional country, Moldavia. It was estimated to be 1.7 million in 2015, and it is estimated to be growing at the rate of 2.4% annually, right? If t equal to 0 represents 2015, find a formula for the population at date t. So here we use the compound interest formula. So the population at time period t, P of t, is nothing but the initial population, P of 0 times 1 plus r to the power t, right? Now the initial population here is 1.7, right? And r here is 0.024. Right, because population is growing at 2.4% annually. So you have 1.7 times 1.024 to the power t. That then represents your population at any time period t. The question now is, what is the doubling time? This is the next part of the question, and this is a concept which needs a little bit of elaboration. Doubling time refers to the amount of time it takes for the quantity in question to double, to become double of what it was, right, originally. So let's see how we calculate the doubling time. This is a very important concept which is used when we talk about exponential functions or any situations that are captured through exponential functions. So our exponential function is given by f of t equal to capital A times small a to the power t, right? And we have said here that capital A represents our initial value. Now let us suppose that the doubling time is given by t star. Okay, that is the amount of time it takes for the quantity to double, that is to become twice of capital A, because initial value is capital A. So if I'm talking of the quantity doubling, it has to become twice of capital A. So we are saying here that f of t star, because eventual value is now twice of capital A. So our equation becomes, just substitute the information in this equation that is highlighted here in blue. So twice of A, that is our final value, double, is equal to the original value, that is capital A, times a to the power t star. I'm putting t star here because that is my doubling time, And you can see here that these capital A's will get cancelled on both sides of the equation, and you are left with the equation a to the power t star is equal to 2. So if you know your fixed factor, your small a, then you can easily solve for your doubling time. Now, one important thing that you must notice here is that in this equation where you calculate your doubling time, this doubling time, if you notice here, is totally independent of the initial time. Your initial time doesn't appear anywhere in your solution. When you solve this equation, your initial time doesn't appear anywhere in this equation, right? That is to say, the doubling time of the general exponential function, it is independent of the starting value. Suppose, let's say we're talking of population, regardless of the starting population, wherever you start the story, for whichever starting population you take, we are saying here that the amount that it takes for the population to double, the amount of time that it takes for the population to double is going to be the same, regardless of the starting population. And that's an important result. So let's go back to our question for Sildavia and calculate our doubling time. So remember, our population in time period t is given by population at time period 0 times 1 plus r to the power t. Because I'm looking at the doubling time, my final value of the population p of t is 2 times p of 0. So you note here the initial populations just get cancelled immediately. That is why the initial starting population doesn't matter when you calculate the doubling time. So your equation becomes, which is exactly that a to the power t star format, equal to 2. So a here is 1 plus r to the power t star is equal to 2. And because r here is 0.024, our equation is 1.024 to the power t star is equal to 2. And you can solve this for t star. You can take logs on both sides or just feed this information to the calculator and see what you get. Here you can solve your doubling time for your doubling time, and you will get 29.23 years as the doubling time, the time it takes for the population to double in Sildavia. Now we can also turn things around. Excuse me. So let me back up, because this is a very interesting rule that we have in finance. This is one of the various rules of thumb that we have in finance. So this is something you can do as an exercise. This is called the 7-10 rule. This says that money invested at 7% per year doubles in approximately 10 years, whereas money invested at 10% per year doubles in approximately 7 years. This is a rough rule of thumb which you can use for when you're investing your money. And here again, the point here is that you should do this as an exercise. How would you calculate the doubling time? The interest rate in the first case is 7%, and you're saying that the doubling time is approximately 10 years. So remember, here a is equal to 1 plus r. So I'll just give you a hint here. So for example, if you're looking at the first result, 2 times k, because k represents a principal amount, becomes equal to k times 1 plus r to the power t star. So your equation that you're solving for is 1.07 to the power t star is equal to 2. And once you solve for t star, you'll get approximately 10 years. Similarly, you can even do the second part of the result. Okay, so as I was saying, let us flip things around and now look at a problem of decay. And here you have a problem where which revolves around a radioactive isotope iodine-131, which has a half-life of 8 days. So here you have the concept of decay coming in, which is to say in 8 days the quantity of this of iodine-131 becomes half of what it was originally at the initial time. Now this isotope iodine-131 is often used to diagnose disease in the thyroid gland. And if there are I0 units of the material at time t equal to 0, the question is, can you come up with an exponential function to show how much remains after t days, how much of the material remains after t days? Remember, the half-life is 8 days. So here you can actually, for the final value, suppose this is the kind of function you're fitting in, I of t is equal to I0 times small a to the power t. Then the final value, because half-life is 8, so if I put t equal to 8, the final value will be half of the original value, which is half of I0 equal to I0 times a to the power 8, right? The I0, the initial value, will get cancelled on both sides. And here you can see we can solve for small a, which is a fixed factor. And this I can do because I get a to the power 8 is equal to half, right? And therefore, a is equal to 1/8 of half to the power 1/8, right? And I can simply just substitute this information into my functional form. So, I of t is equal to the initial value I naught times half to the power 1/8 times to the power t, because 8 has to be raised to the power t. So, this becomes half to the power t by 8. So, this illustrates a case where you have exponential decay. Now, we can also talk of what is known as a generalized exponential function. So, let us just generalize things, which is to say that suppose I multiply the exponent. Let us start by the function with the function a to the power t. If I multiply the exponent by a constant b, or if I attach a coefficient capital K to a to the power t, then what will happen to the function? So, my generalized exponential function is given by y equal to k times a to the power bt, right? Now, to see how things change, I have given you an illustration here. I'm looking at the graph of 2 to the power 2t, which is nothing but y equal to 4 to the power t, and we're looking at how we can get this graph from the graph of y equal to 2 to the power t. Now, the graph of y equal to 2 to the power t is given here in blue. It passes through 0, 1. The graph of y equal to 2 to the power 2t, we can see here is a compression. It has been compressed to the left, right, in such a way that it is now halfway between the original graph y equal to 2 to the power t and the vertical axis. Now, why is that? Let us see, and also note here that the new graph is also passing through the point 0, 1. 0, 1 is a point on both graphs. Now, how is that the case? Remember here I told you that exponential functions lie everywhere above the x-axis, so that your range is the open interval 0 to infinity, right? So, any value that I take on the positive side of the y-axis must lie on both these graphs, right? So, if I take the value, let us say y naught, that is going to lie on both these graphs. Now, let us suppose if we take the original function 2 to the power t, and let us suppose that is equal to y naught for t equal to t naught, okay. Then, if I take the new function 2 to the power 2 times t1, what is the value of t1 for which the graph will have the same value y naught, okay. Clearly, that t1 has to be half of t naught, because the value is the same. So, to make 2 to the power 2 t1 replicate this 2 to the power t naught, I have to take t1 equal to t naught by 2, so that the 2's get cancelled. And that is precisely why this new graph gets compressed halfway between the original graph and the vertical axis. So, here we have the result that doubling of the exponent, for example, has the effect of compressing the exponential curve halfway towards the y-axis, and vertical intercept is clearly not affected. There is this compression, but it's compression of a zero distance, which is 0. Similarly, I could halve the exponent. Halving of the exponent has the effect of extending the exponential curve away from the y-axis to twice the horizontal distance. You can check this out for yourself. Again, the vertical intercept is not affected. This other kind of shift that I wanted to talk about is where you're attaching a coefficient to the original graph, which is 2 to the power t. So, if I ask you how would you obtain the graph of twice 2 to the power t from the graph of 2 to the power t, then this is nothing but, again, it's a shift, but now it's a vertical shift. So, when I double the coefficient, that will have the effect of extending the exponential curve. Earlier, remember, it was a horizontal shift. Now, it's a vertical upward shift, which is to say that for any value of t naught, the value of the y on the new function would be twice that of the value on the original function, right? And here the vertical intercepts, as you can see, have also changed. The vertical intercept of twice 2 to the power t is twice, 2 times the vertical intercept of the original function. Okay, so that is as far as a generalized exponential function is concerned. You can always manipulate your graphs. But the lecture would be incomplete if I didn't talk about the natural exponential function, where we take the base as the number e, which is perhaps the most important base that we have in an exponential function. E, as you would know, is nothing but an irrational number, which is slightly larger than 2.7. As you can see here, I've shown you the 15-digit expansion of e, and the graph looks exactly like the general shape of the exponential function that we have. You can do these exercises on your own. How would you draw the graph of e to the power minus x, starting from the graph of e to the power x? As you can see here, this is just a reflection of the graph on the other side of the y-axis. Similarly, how would you get the graph of minus e to the power x, starting from e to the power x? That is also a reflection, but now on the other side of the x-axis. You can try these questions. Okay, and now I would like to, as the last part of my discussion, I would like to go back to the question that I had posed in my previous lecture. I've just slightly manipulated it. So let's just revisit this. So I am giving you two options. One option is that you get rupees 10 crores in your bank account after 30 days. This is one scheme. And the other scheme that we are giving you is that 1 rupee will be deposited in your bank account on the first day, and that 1 rupee will double every day for the next 30 days, and you will get the amount realized after 30 days, right? So the question that I posed to you was, which option, which scheme would you like to go for? So here the answer is option B. If you're going to go for option A, which sounds tempting because you're going to get 10 crores after 30 days, which is again a lot of money. But if you go for option A, you're going to clearly miss out on a lot of money, which is here, right here for you to see. So what happens is, if you're going for option B, what happens is, see, look at the way your money is growing. This is exponential growth. Day 1, you start with 1 rupee. Right? Day 2, it becomes 2 rupees. Day 3, it becomes 4 rupees. Day 4, it becomes 8 rupees. Now just look at the way things are moving. This is on day 3, you have 2 to the power 2. On day 4, you have 2 to the power 3 as the amount in your bank. So day 30, the amount in your bank is going to be 2 to the power 2 to the power 29, right? Because it's 1 less. The power is 1 less. So that, if you use your calculators, just pull out your calculators and do your calculation, that is 53.7 crores approximately. So clearly you don't want to miss out on all this money as compared to the 10 crores you were getting in option A. So here one would go for option B, and basically the main takeaway from this example is that even though you're a student, even if you have less money, but it's good to start investing, even if it is in small amounts. Start investing early, start small. Invest regularly, because your money is going to yield good returns at a later date. We have to use the power of compounding. So the earlier you start investing, the better it is, even if it is in small amounts. So that's all for this lecture on exponential functions. Thank you.